So continuing on from the previous video, what we're looking at here is this example. Okay, so we have two fixed temperatures here on the ends. These are the heat sources, and we've got four internal nodes, T1, T2, T3, T4. And we're going to estimate, I should say, the temperatures at these points, 0.2 seconds after the heat source is applied when the initial temperatures are 0. Okay. So the equation I'm using is this one. It's the next value of the temperature in time is the previous value of the temperature plus lambda, which I'm approximating to 0.021 for the purposes of sanity, then times the next temperature over in terms of distance minus twice the current temperature plus the previous temperature in terms of distance. So this is the formula that I'll be using here. Okay. So the next one I'm looking at is T1, 1 for distance, 1 for time. The initial temperatures of all of them is 0, so this is equal to 0 plus the lambda, which I'm approximating as 0.021. And then what goes in here is the next temperature over, which is T2, and the previous value of T2 is 0, because we said we're starting them all at 0. I might write something about that above. Minus twice, using that formula, twice the current value, which is also 0, plus the previous temperature in terms of distance, which is 100. So what I might write down above here is the initial condition for all possible distances that are not 0 or 10. At time equal to 0, the temperature is 0. Okay, so what we see here is, when we actually do the maths, there is a heat flow from here to here, which causes it's a net heat flow, which this temperature is going to rise. So doing the calculator, 0.021 times 100. And this is 2.1, and this approximates the temperature at let's say 2 meters along the beam at time 0.1. So we'll do the next one. We'll do all these. Okay, so next one is T2. So the next temperature here at time, the first time, which is 0.1 seconds later, is equal to the previous, which is 0, plus 0.021. The next temperature over in terms of distance, which is T3, and the previous value of that was 0. I might have to write something else above here. Minus twice the current value of that temperature. Yeah, we better write this above. So T10, that's the initial temperature of T1, is equal to T20, the initial temperature of T2, equal to T30, the initial temperature of this, equal to T40. All of these were 0. That's where I'm getting these zeros. Okay, so this is 0 plus 0.21 as 0 the next temperature over minus twice the current temperature plus the previous temperature and distance. Now you don't use this new value, use the previous value, which is 0. And this is 0, this is 0, so you get, there essentially isn't enough time for heat to transfer from here to here. Of course, that's ridiculous. There's going to be a little bit of heat transfer. If you want to see that after 0.1 seconds, you have to use a smaller time step size. But anyway, here we don't see it. So this is the approximation of the temperature at 4 at time 0.1. Now, of course, the next one's going to be the same. I'll just talk through it, but a little bit faster. So the formula on the previous page says the next temperature for T3 is the previous one, which is 0, plus lambda, which is approximately 0.021. I've introduced rounding error, which is bad. Then it's the next value, which is T4. The previous T4 was 0, minus twice the current temperature, which is which is 0, plus the previous temperature, which is T2, and the previous T2 was 0. And this is also 0, and this is the approximation, the temperature at a distance 6 along the rod at time 0.1. And now we've got one more, T4 equal to, now what we should predict is, because the temperature difference between these two, 100 and 0, is twice the temperature distance between these two, So this temperature should be twice as big as this one. So we're expecting to see 1.05 down here, but we'll see it in the maths. So T4 at the first time is the previous T4, which is 0, plus 0.021 is the lambda. The formula says the next temperature over in terms of distance, which is this 50, minus twice the current temperature, which is 0, plus the previous temperature in terms of distance is T3, and that at the previous time is 0. So this is 0.021 by 50. As predicted, 1.05. This is approximately the temperature at 8. Distance 8 is 0.1. Now, one thing that's worth remarking here for the purposes of VBA, you will have to take these previous values off the worksheet, or you will have to define a T-old variable. The other thing, when you're doing this in VBA, do not round this. Do not introduce rounding error into VBA when there already is rounding error there. Okay, now let's do the next one. So we're going to iterate this one more time. Obviously in VBA you keep going. So T1 at the next time. So it's equal to the previous temperature, which is 2.1, plus 0.021. The formula says it's the next temperature over in terms of distance. That's T2. And of course that previously was just 0. Minus twice the current temperature, but previous time, which is still the 2.1. Plus the previous temperature in terms of distance, which is 100 at the previous time. Well, that's always 100. Now, what we can see here is there's kind of something relatively interesting. So what you're going to basically get here is that because T1 has risen in temperature, the temperature gradient is now smaller between T1 and this boundary. And because of that, this number is getting a little bit smaller. So this isn't going to be 4.2, it's going to be slightly smaller. Okay, let's go. 2.1 plus 0.021 times minus 4.2 plus 100. I'll just go with, because I'm only doing it twice, I'll just do 3 significant figures. 4.11. So it was less than 4.2 because it increased in temperature a little bit, so there wasn't as much as a temperature gradient, so there wasn't as much of a heat energy flow. So this is an approximation of the temperature at that point, which is x equal to 2, at the time 0.2. So what's going on here is, so if you imagine this from the previous thing, we had the initial temperature distribution. In this here, we've calculated the temperature after 0.1 seconds, and now we're going to calculate the temperature after 0.2 seconds. Now at the end of this, we'll say, when should you stop? Okay, let's go again. Next one, T22. So the formula says it's the previous temperature, which is 0, plus the lambda, which is 0.021. Now what do we want to do is the next temperature over is T3, and the previous T3 was 0. We're always using the previous value. We're always using these ones. So this is this picture. On the previous page, when you're trying to find out what's happening at the next point, you use previous time, which always means previous in this sense. Okay, so minus twice the current point we're interested in is this T2, and the current value of that is 0, plus the previous in terms of distance, and the previous in terms of distance is T1, and the previous value of that was 2.1. So what we're seeing here is there's a little, initially remember both of these were 0, so there was no heat transfer because there was no temperature gradient, but now after 0.1 seconds, according to this is around 2.1, this is 0, so this is hot, this is cold, you're expecting some heat transfer from here to here. We'll see what the thing says. We'll go with we'll go with 3 significant figures. 0.0441, that's actually equals. So this approximates the temperature at distance 4 at time 0.2. We'll do the next one. T32 equals previous, which is 0, plus lambda, which we're approximating as 0.021. Oh, this great blue pen is dying. Right, next value to in terms of distance is T4, and the previous T4 is 1.05. Minus twice the current in terms of distance, well, the current is T3 and the previous was 0, plus the previous in terms of distance, which was T2, and T2, the previous value is 0. And well, let's see what we get out here. 0.021 by 1.05. Again, it's because there is a temperature gradient between T3 and T4. You're going to get a, this was 0, this is like 1 degrees. You're going to get some heat transfer going in that direction. I'm getting to 3 significant figures, 0.0221, and this approximates the temperature at distance 6 at time 0.2, and one more. So here we're going to see, again, we're going to see some heat transfer from this hot thing to 1.05, but the temperature difference is a bit smaller this time than initially, so it's not going to be as large as 2.1. Now, of course, what's going to happen after a while is that you're going to have a heat flow coming from the other end of the rod. Previous T4 is 1.05, plus the lambda is 1.02, excuse me, 0.021. Next temperature in terms of distance is the boundary temperature 50 minus twice the previous value of this temperature, which is 1.05, plus the previous value in terms of distance, which was T3, the previous T3 was 0. And let's see what the calculator says to this. We'll just go do 3 significant figures. And we're expecting this to be smaller than 2.1. Yeah, a bit smaller, 2.06. And that is an approximation to the temperature at 8 at time 0.2. So you keep, obviously by hand this is nonsense, but you do this in VBA. Now the thing that you have to understand is, when do we keep iterating this until? And what you want to keep on going is until, well, this is what happens. So this is distance. Now things are a bit more complicated if the rod is not insulated, but in any problem I give you will be insulated. Oh, I kind of missed it. All right. So this is distance 10. It goes from 100 to 50. And this is the equilibrium temperature. You can actually see this from the heat equation itself, because the steady state, so what you're getting is you kind of got a, say after 2 seconds, your temperature might look something, it's basically something like this, roughly. And that might be the exact answer. We're not quite there. But anyway, something like that. Anyway, so the temperature is going to keep rising. And in VBA, you might be able to do the dynamic graph, which is really cool. So you can actually see the temperature increasing from 0 up to this. And this is the steady state. Now, we have mentioned in a previous video that this has to be a straight line, but you can see it here if the rod is insulated, because in steady state, the temperature does not change in time. So this is equal to 0. That's what steady state means. And a second derivative equal to 0 means a straight line. And you know that it's 100 here and it's 50 here. So it has to be like this. Now, write it in the form mx plus c. Oh, I forgot the blue dyed. So the slope is rise over run. The rises, it goes down by 50, so it's minus 50. Over the run is 10, so it's minus 5x plus 100. And you bang in x equal to 2 into this. So we're looking at 2, 4, 6, 8. So bang in 2 into this, I believe that you will get 90, 80, 70, 60. So this gets closer to 90. This gets closer to 80. This gets closer to 60, and this gets closer to 50. And from the theory, you know that it will get closer and closer. Now, in theory, it takes infinite amount of time. So what you want to do is keep going until it's within, I don't know, 0.5. So you want to keep on going until, so if this is your VBA, so you keep on going until, say, the absolute value of, say, temperature 1 minus its equilibrium, which is 90, is less than 0.5. So that means you're to one significant figure, it's there. Now the thing is, you have to and, because it's possible for one of them to converge and not the others. So you need t2 minus 80 to be less than 0.5, and etc. And the convergence will be very nice like this, as long as you keep the lambda less than or equal to a quarter. If the lambda is a bit too big, you can kind of get really weird stuff happening that I'm not going to even think about right now. So that's how it goes. So you should be able to do lab 8 now. Thank you.